For any newcomers to CERCA, I'll take a minute to introduce CERCA. It was formed about 2.5 years ago at IIT Delhi with the objective of doing research and providing feedback and information to policymakers for air pollution abatement. A lot of work has been done in that area in the last couple of years, and CERCA has sort of established its name and its expertise of having IIT Delhi faculty get involved in addressing this very important problem of air pollution. Earlier this year, we decided to expand the scope of CERCA to include climate change. So our work going forward would cover both air pollution and climate change. And as you would know, they are sort of linked in many ways. So it's a very logical area for us to sort of expand our scope of our activities. And the monthly lecture series has been instituted for several months now. It's very important activity of CERCA, popular activity of getting some distinguished speakers to address people who are interested in air pollution. And we are delighted that we are having this lecture today. So with that, Sagnik, shall I pass it on to you, or Hemant is there to introduce the speaker?
No, I will do that. Thank you very much.
Thank you.
Yeah, thank you, Mr. Duggal. So it's a pleasure to introduce today's speaker, Dr. Pawan Gupta. Pawan is a good friend, and it's a real pleasure to host him for this important webinar. Dr. Pawan is a senior scientist, Earth Sciences at the Science and Technology Institute, University Space Research Association, NASA Marshall Space Flight Center. He has completed his PhD from the University of Alabama in Huntsville. His main research expertise are in the field of aerosol remote sensing, application of satellite datasets for air quality monitoring and assessment, air quality in growing megacities, understanding the climate impacts of air pollution, developing statistical and machine learning models to estimate surface level air quality using the satellite data, and many others applications for remote sensing. Currently, Dr. Gupta is a member of NASA's MODIS and VIIRS science team, citizen science team, and measures team. He also participates in developing and conducting remote sensing technical workshops and capacity building activities for the NASA Applied Science Program. I am sure many of the participants today have attended Dr. Gupta's workshop as part of NASA's ARSET air quality team. He has been very active, and he has been giving training to across the world, in fact, how to use the satellite data for climate studies and air quality studies. And he's also lead, and in fact, he is actually lead of this NASA's ARSET air quality team, and he serves as the portfolio manager for Survey's applied science team. So with this brief introduction, I now invite Dr. Pawan Gupta to give his lecture.
Sagnik, thanks for all those kind words, and thank you, Mr. Duggal, for the opportunity. As Sagnik says, we have been known each other for a long time and collaborate closely. So it's my really pleasure to speak with the at IIT Delhi, where we actually do a lot of our work in collaboration with Sagnik and other people. Okay, so if everyone is able to hear me okay, I can start my talk for today. Great, thank you.
Yes, yes, clear. Yeah.
Let me share my screen. Okay. Are you able to see the screen?
Yes.
Okay, great. Thanks, Agnik. So today I'm going to talk, as Sagnik mentioned in the introduction, I'm more of a person or scientist who worked a lot more on the data development from the satellite, and less of that application. We do a little bit application, but a lot of my time actually goes into developing data product, assessing their quality. So I will talk more on the data aspect a lot more today than the actual application of the data. Now, I'll give you some example also. And as Sagnik mentioned, I also spend a lot of my significant time in training air quality professionals all around the world in how to use the satellite data. So please excuse me, some of my slides may be too basics for the audience here, but I just wanted to make sure that everybody is on the same page when we discuss some of the details. So with that, let's see if we can move on. So when we talk about the space-based observation, which are relevant to air quality, our current capabilities are in both sector, gases pollutions and the particle pollutions. In terms of the gases pollution, we do have some capabilities, and depending on the specific gases and accuracies and coverage, it varies from region to region, from specific gases to gases. But some of these are listed here, like ozone. We have very limited capability just because it's very hard to do surface level ozone extraction from the satellite data. As you know that most of the ozones actually is in the stratosphere. But then we also have some of these anthropogenic emissions which happens pretty frequently, NO2, SO2, methane, formaldehydes. So some of these measurements are done mostly using UV spectroradiometers, which are placed in many different platforms, and we do get some data. But today's talk, I'm going to focus more on the particles or aerosols or particulate matter. And there are two main, when we talk about the aerosols, there are two main things which we often refers to it when it comes to the air quality or the climate. One is the column loading, how much aerosols particles are there in the entire column of the atmosphere, AOD, and then the PM 2.5 and PM. So I will focus more on the particle pollution today and the relevant data sets from the satellite and ground and modeling perspective. Okay, so just to very briefly to give you this is a busy slide, but what you see here is a complete system where you have on the ground or the source of emissions, which either directly emit these particles in the atmosphere, or the precursors like NO2, SO2, and other gases are emitted in the atmosphere, and then they convert into aerosol by secondary by gas phase chemistry, which happens in the atmosphere. So once the emissions are happened, particles are in the atmospheres, and as we know, there are other things in the atmosphere like cloud, incoming solar radiations, gases, and other things, and they interact with each other. And when they interact, a lot of things happens. One is visibility reduction, which is most obvious to any common people, which actually you can see whenever there are large concentration of this particle, we see the impact on the visibility. There are also aerosols also serve as a cloud conditioning nuclei for the cloud formation. So they are very, very critical to precipitation activities. And then they also have impact on incoming solar radiation and outgoing long wave radiation from the Earth, which can impact the Earth radiation budgets or energy budgets and have an impact on climate and long-term climate change. So the range of impact of these atmospheric aerosols varies, and depending on what we are trying to understand, they can be classified into many different ways. But today, since we are talking about the air quality, so the most important impact is on human health. So when the particles injected into atmosphere and stay close to surface, which means at our nose breathing level, then we are more concerned about their health impact. And that is what I'm going to talk today more um, with respect to the columnar loading also, which is what we get from the satellite. Okay, so if we divide those that big chart classify into big categories, then the atmospheric aerosols have three different types of major impact. They do climate impact on climate. They do impact on weather as well. So weather means what is happening on a daily basis or within a day. And then the third is the air quality. So I'll focus mostly on air quality. So what is when people say air pollution monitoring or air quality monitoring and forecasting, what it involves? So one, the most critical part of that is the ground measurement, because that's where you get the uh, highest quality of the data, and that is very, very critical for making accurate measurement and assessing the concentration of particles on near the surface which we are breathing. So the ground measurements are very, very critical component of this whole puzzle, or it's one of the tool, I would say, in air pollution monitoring or management. Then more recently, in last couple of decades, we have started exploring data coming out from the space-based observations or from aircraft, so which includes satellite data of aerosols or particles, which have become an integral part of air quality analysis and forecasting systems in current time. And they do fill a lot of data gaps, which we are seeing in the ground measurement. And then the third and most important component, because monitoring and just measuring is one part, but uh, if you really want to use it, then you need to forecast. Forecast means what is happening, going to happen 3 hours from now, 1 hours from now, or tomorrow, or 7 days. So it's very similar to what weather forecasting. If you have that information available to the public can make decision about their activities to reduce the exposures to the pollution. So the air quality management, which include both monitoring and forecasting, has these three components which are very, very critical in making sure we understand the science, we are able to make accurate measurement, and we are able to forecast what is going to happen in the future or near future. So these three components, I'll start and try to cover these three components in today's talk. So first, let's start with the ground measurements. When I say ground measurement, as I mentioned earlier, most people are familiar with this term PM 2.5 and PM10. In earlier, when air quality studies started, agencies, environmental agencies, or pollution control board all around the world um, started making measurement of suspended particle mass concentration, RPM or SPM they used to call it. Right now, as we started understanding their impact on health, we try to started segregating them into different size. When we start with PM10, which is a coarse particles with aerodynamic diameter less than or equal to 10 micrometers. So one thing I want to note down here is that this PM, when you say 10 micrometer, it's not a geometrical diameter, it's an aerodynamic diameter, and it is done to make sure the measurements are consistent across the globe and across the measurement techniques. And then the PM 2.5, which are very fine, they can penetrate deep into your lungs and different parts of the body and can create different kind of health impacts. And this picture just showing a graphical representation or a visual how tiny these particles are as compared to human hairs or sand, which give you a visible perspective on the very, very fine small particles, which are very difficult to see from the naked eye. Okay, so to make measurement of these particles or something we called mass concentration, which is a mass per cubic meter in a unit volume. So it's typically we make measurement in microgram per cubic meter for these particles. And there are two ways to do from the ground. One is the standard monitor which are very expensive. They can cost anywhere from $20,000 to $50,000, and then management cost is on top of that. So these are very accurate, within 5% of the measurement error, which are shown on the left. And we have a standard. All countries, most countries actually who make this measurement, they have their own standard. Many of them follows US EPA, some follows their own standard. But if you look the market in recent, I would say 5 to 7 year time period, there have been flood of these low cost monitors which are in the market, in which can make measurement of these particles and other gases which I'm mentioning, and they are very, very low cost in terms of their price. Means you can buy a monitor as cheap as $20 to $1,000 depending on the quality and what function it does. So what I'm going to talk next is basically we'll talk about some of the data quality concern which we have from these low cost sensors. And for that, we about 4 years ago, NASA funded us a project called Citizen Science, Air Quality for Citizen Science, using citizen science approach. And this is led by Prakash Doraswamy from a RTI institute here in North Carolina. And if you look the if you look your proposal team, then you will see that as a part of this team, IIT Delhi is a partner. We are working closely with Sagnik. He's helping a lot with deployment and other people in India. So there are two major goals of this whole project. One is to assess the quality of these sensors, how good they are with respect to the reference grade monitors. And the second one is, can we integrate this low cost sensors data, because they are large in number, with the satellite data to further improve our understanding of the satellite data, and possibly combining these two data sets to create a more regular maps of pollutions in places where we do not have any kind of a standard measurement. Those are main two science goals. But in addition to those goals, we had and the approach which we took here is how we can engage individual citizens so that we can improve their awareness, as well as we can use we can collect the data by reducing the resources required for any scientific data collection. So we distribute these sensors and then collect the data through an online system, and that give us opportunity to analyze further the data. Okay, I think I'm not slide. Hold on, for some reason. So this some kind of tool just started. Okay, now it's good. Sorry. So as a part of this project, we have deployed these sensors in 3 different locations. As I was showing earlier in the earlier slide, these are the 3 regions we selected for this experiment. One is Los Angeles area in Southern California in US, Raleigh in North Carolina on the East Coast, and then the Delhi or the IGUP region in India. And the reason we selected these 3 regions are because of the relative concentrations of particulate matter or aerosol in this region. So India being a super polluted regions, Raleigh is super clean conditions, whereas the LA represent more somewhere in between the two moderate polluted conditions. So we wanted to see how these sensors perform in different environmental conditions, different loading of aerosols, and different climatic conditions. So Again, these are the locations of the sensor deployment: North Carolina, the California, Raleigh regions, and then in India, we have already deployed about 70 to 80 sensors, and more are coming online in few months. Okay, so first thing we did is before deployment, we did a calibration effort. So to do calibration in India, we did at IIT Delhi, where we actually put out about 100 sensors just next to a federal equivalent method, which is a BAM sensors, and ran the experiment for several weeks. And then we compare the data with and see how good we are getting the data. So the top left plot shows a PM2.5 comparison between purple layer on the y-axis and the BAM on the x-axis. And what you see here is without any correction, this is the raw data just directly coming from the sensors. It does pretty high degree of correlation, although there are biases, the slope is not 1-to-1. And as you can see from the data, there is a spread, and this spread is coming from different units. So this is very critical to understand that although all purple layer sensors units are manufactured and supposed to be identical, they do produce different data measurement at given time, even though they are operating in the same place. So there is a variability among the sensor, which can be very, very critical if we are not aware of while interpreting the data. So that is one thing. We did the same thing in North Carolina. And you can see the range of concentration. In India, it goes all the way up to 600, whereas here is typically goes beyond 10 when there is 10 or 15 microgram per kilometer. And then both of these are measurement during the January time. So there's a huge difference in the concentrations and so the performance as well. So we developed some machine learning approach to actually make some of the corrections so that all sensors are consistent. And we did that. And once the data is corrected, then this is the new data which we see here on the right side. So we are able to produce better quality data. We are still experimenting. We are working on a publication for this analysis. And like I said, IIT team is heavily involved in all this aspect. So the other aspect which I was talking earlier is about the quality or the intersensor variability. So if you can see here, on x-axis we have a PM2.5, and then the y-axis is typically a bias, which is a purple layer minus FEM. And this experiment we did in California, where we have 6 different sensors, and if you see that this different line shows different sensors. So you can see there is an increase in bias as a function of PM2.5, specifically in California, but there is a spread among the sensor. So this bias, as a scientist, I'm fine to actually account for this bias or correct this, but this variability among the sensor is more dangerous, because if we don't understand this before deployment, then this can create large disparate discrepancies in the data, and it will become difficult to assess for us after the fact which one is correct. So we need to make sure that we understand this differences when we're using the small or the low cost sensors. So when we talk about the current global monitoring, this is a non-profit efforts here in US, which actually collect data from all kind of regulatory grade monitors from the around world, and they provide into a nice web for everybody to actually download and use the data called OpenAQ. So you can see from the coverage that it does have huge gaps all around the world, especially African continent, South America, Southern Hemisphere, and large gap actually in Asia as well. There is another efforts which is out of Washington University now, started at Dalhousie in Canada, and that is called Spartan. So this is a effort actually specifically designed to understand the satellite and ground measurement connections and making the chemical speciation measurement using a specific instrument. So this network is growing. And then this is the purple layer network, which has almost close to 15,000 monitors all around the world now, which is a low cost sensor, but it does provide useful information. Okay, so let's see what satellite can offer us, right? So we talked about the ground. Now let's talk about the satellite. So there are, before we get into the satellite, there are multiple types of satellite. There are geostationary satellite, which provides frequent measurements at given region, every 5 minutes, 10 minutes, even less than that. And then there are polar orbiting satellite, which basically provides once in a day measurements and once in a night time for other parameters for air quality, only daytime measurements. So these two types of instruments, polar orbiting, have been in the service for a long time. Geostationary for air quality are becoming more reality in recent times. And then there are other types of sensor which are specifically, we are still experimenting, called L1 orbit. So if those who are not familiar with the L1 orbit, it's a orbit about 1.5 kilometers away from the Earth. So this can actually see, if you put any satellite there, it can see moon and Earth all together. And this is one of the sensors is there looking down, called Discover or the API. And this sensors provide imagery or spectral measurement of lighted area of Earth every 90 minutes. So every 90 minutes you get about 20 kilometers spatial resolution. And so this is very, very useful and unique data which we have access now in more recent time, which were not possible before. So in future, there may be possibility to put more satellite at that kind of orbit to actually get more frequent data for the entire globe. On the right is just showing an example of the fires which were burning in Canada in 2017 August, and the fires were putting a lot of smoke up in the stratosphere. And this one of the parameter we call aerosol index is, if you look the values which are really, really high, larger than 20, it does shows that they are up, very up in the atmosphere and in high concentration. So just an example. And then there are new generations of satellite which you might be hearing more, called commercial satellite. These are CubeSats, small satellite. They can weight anywhere 5 kg, few kgs to 10 kgs. And commercial companies are actually deploying these satellites in hundreds and hundreds of numbers. The good thing about these satellites are that they provide very frequent measurements and very high resolution. So this specific pictures is taken by a satellite called from the Planet Lab. And this Planet Lab satellites actually have a resolution of 3 to 5 meters. Although they have only few spectral channels, there are issues with the calibrations, and there are other inter-satellite calibration issues because there are large in numbers, and then when they generate the data, they combine the data from the multiple satellite. But they have capabilities. So just in this example, what you see here, there was a controlled burn happened near the Washington DC last year. And when we look this fire, smoke coming from this fire from Modis Terra and Modis Aqua, which are two main sensors, making measurement in morning and afternoon, then you can see the smoke plume coming out towards the Washington because of the wind direction. But when you look from the planet data, then you can see really super high resolution actually zoomed in into the area, because these are, and you can convert these into a PM 2.5 MAM. This is a very, very early stage. We really don't understand this data a whole lot. There are only few studies so far which have explored this data for air quality studies, and this data is not free for public to use. This is still a commercial satellite, so you have to buy the data. Okay, so what do we get from the satellite or the ground? The other parameter which is very critical, which we often retrieve from the satellite and has been used a lot in climate studies. We call it aerosol optical depth. It's a very similar as PM2.5 in many ways, and there are differences as well. I'll go through that. So it's basically an optical property. As incoming solar radiation passes through the atmospheres, the radiation attenuated due to the scattering or absorption by aerosols particles. So this is nothing but a attenuations of solar radiation. It is always measured at certain wavelengths, and its value really depends on where the particle in the atmosphere, what kind of chemical composition they have, their shape, size, and at the wavelength at which you are making measurement, because it is sensitive to the size of the particle. So this quantity can be measured from the ground monitors, as well as it can be you can get it from the satellite data. But this is just want to introduce the quantity before we get into it. So if we add this aerosol optical depth measurement from the ground, then we have these 4 different types of measurements, global network, which can actually provide you a lot of good data from the ground perspective. So this is the AeroNet measurement, which is make measurement using sun photometer at 10 different wavelengths. And there are 400 plus monitoring stations actively managed by NASA. And the primary purpose of the AeroNet is just to validate the satellite data. Okay, so like I said, I work a lot with the algorithm development and evaluation, and the specific people who are familiar or using the satellite data for aerosols, they know there are many, many different algorithms which operates on not only on one satellite sensors, but multiple sensors. So in the beginning, when this MODIS was launched in 1990 on Terra, there was only one algorithm called dark target land and ocean algorithm, and that algorithm was operational in the beginning and still continue to be operational. It produced the data at 10 kilometer and 3 kilometer. Over the time, to compensate some of the problem in dark target, or to have a better way of retrieving aerosols, there are new algorithms which came along. So deep blue algorithm came along 5-7 years after the dark target, and then more recently, last 5-7 years ago, Maya, which provide data at 1 kilometer came along. And then other agencies like NOAA and even in India, ISRO has their own aerosol retrieval algorithms which operates on different sensors. So the dark target, currently we are running on 6 different sensors, 3 polar orbiting, which are listed here, 2 MODIS, 1 VIIRS, and then we have 3 geostationaries. One goes our series of satellite goes east and goes west, and then the Himawari, which is over Asia. The algorithm was initially developed by Kaufman and Tanre. Later, lot of people have revised the algorithm, including Rob Levy, Lauren Remer. I did contribute in different ways throughout as a part of the science team. So we have been applying this algorithm. We understand the data, and now we are trying to get to the next step, how we can actually combine this data from the different sensors. So let me just give you a little bit more about the data quality from the dark target algorithms, and then we move on. So if you look the dark target aerosol retrieval evaluation or validation across the globe, then basically we use AeroNet as our primary source of validation. And what you see here is a comparison between AeroNet on x-axis and MODIS AOD from this Aqua satellite, which is an afternoon overpass on the y-axis. And this is a global comparison, okay? And the accuracies are defined as about 20%. So there are 2 products. One is 3 kilometer resolution and one is 10 kilometer resolution. So you can see the accuracies, expected uncertainties for 3 kilometers is a little bit higher compared to 10 kilometer. And that is because higher resolution creates more signal to, we have less signal to noise. So there's a higher noise actually in the data in that creates. So the correlation is about 0.87, and then on MODIS 10 kilometer product, we have a correlation of 0.9, which shows a little bit better improved accuracies. So if we move on, then as I showed you earlier, the MODIS does have a 20 years of data records. It was launched first in 1999, and then another sensor was launched in 2002, which continuously providing the data. But over the time, these sensors are designed to run for 3 to 5 years, and we are in the 20s years. So there is a significant changes in the calibrations or because change in the orbit and other things, change in the sensors optics, we have to consistently monitor the data quality throughout the time period before we use them for a specific analysis. So on the left, what you see here is the bias on y-axis. On the x-axis is the Aeronet AOD. So how the bias is changing with respect to the AOD. And you can see that the blue line is aqua, red line is Terra. Terra is always higher than aqua. So bottom line is that Terra is positively biased compared to MODIS aqua. And this is both happens over land and ocean. And there could be two reasons now, because Terra is making measurement in the morning and Aqua is making measurement in the afternoon, which is about 3 hours apart. It varies from place to place. So are these comparison natural, or they are coming because of the sensors calibration issues? Since we are comparing with the Aeronet, it more suggests that they are more related to the sensors calibration fits. On the right side, we have done the similar analysis, but in form of a time series. This is a global mean time series over land in the top, on the ocean on the bottom. And this particular line which you see here is nothing but the difference between Terra and Aqua plotted on the secondary y-axis. So if you look these numbers, they're pretty low, 0.02, 0.03, but as you can see from Terra over land, these numbers are much more varying dynamically on after 2010, similarly over ocean. So this suggests that the Terra over the time is degrading or its calibration is affecting its aerosol retrievals. So the current version of the data, we still are making actually efforts to make these corrections, but the current recommendation from the science team to use this data for trend analysis is that we prefer using MODIS Aqua than the Terra because of this consistent bias. Most likely this is due to the calibration. It could be natural, but we don't fully understand. But the current analysis suggests that it is calibration error, and potentially there may be ways to correct it. Okay, so now let's move on to some other data sets which we have created. This is people again who use MODIS data, Aerosol data, they know that there are different levels of the data. So the level 2 data, which I was showing earlier, created at 10 kilometer and 3 kilometer, but they are swath data. They are much harder to handle, large in volume, and only an advanced users can actually use that data for analysis purpose. Lot of users rely on level 3 data, which are graded, means averaged over larger spatial scales or larger time windows. So that data is currently operational at 1 degree resolution, and that can actually create a lot of misuse of the data for studies which may not be actually required, which may require high resolution of data. So in this example, what we are showing, trying to do actually is creating better high resolution graded data sets. Just to show an example here, this is a Washington DC AOD map at 1 degree. So if you look that map, then you will see that around DC area or in suburb of DC, the AOD is consistently less than 0.18, and it's pretty smooth across the region with some lows and some highs. As you start increasing the resolution, spatial resolution at 0.5 degree, quarter degree, and 0.1 degree, which is close to the native 10 kilometer resolution in level 2 data, then you will start seeing gradients in aerosol optical depth or different hotspots popping up around different area of the city. So if you are interested in city level air quality or city level aerosol optical depth measurement distribution, then you don't want to use that 1 degree product because it is significantly smoothing the values and over the region, whereas the 10 kilometer product actually, or the 0.1 degree product, is going to provide you more detailed information, more accurate, close to the reality. So that is why we created this product. It's available. I'll show you some validation results of that. And then if you look in terms of the coverage, global coverage, right? So on the right side, what we are showing here is an example of how much coverage it is available globally. So although we say it's a daily global coverage, but as you know, there are clouds, there are ice on the surface, and those are the condition where aerosol retrieval doesn't happen. So on a given day, if we are just talking about combining even multiple algorithm like deep blue and dark target, then on average we only get about 8 to 10% area on the Earth's surface, both land, ocean, where we have the data available. So just to remember that daily coverage doesn't mean you have data on every single day. And this is just from the one satellite. If you combine multiple satellites, then we'll see that we can significantly improve. Again, a validation of those 0.1 degree data product using Aeronet. There's a tool to download the data, and there is also a tool to look for individual validation results for our specific station. I'll not get into details. Just want to say that the results of validation are very consistent as level 2 data. So there's a consistency between level 2 and this high resolution graded product. Okay, so the next question is, now we have these so many sensors on from where we are retrieving aerosol optical depth, how we can use them or how we can combine them in a systematic way that we can get more better global coverage on a daily scale. But since the geostationary provide you every 10-minute measurement, can we achieve a more global 30-minute or 1 hour product, which can actually provide some skills to understand the diurnal cycles of aerosols or air quality or their impact on the climate forcing. So to do that, what we have done here in this particular project, which was started a few years back, and we are now in the stage where we are going to provide a data product globally, which will be gridded at 1/4 degree resolution, and it will have a 30-meter time resolution. And here is just an example. So on the top, you have 3 geostationary, goes east, goes west, Himawari, looking different parts of the world every 10 minutes. And on the bottom, you have these Terra, Aqua, and weird sensors, which are looking globally, most likely once per day. And when you take the data from all these 6 sensors and put together using some data fusion technique while making sure we are using correct and they are consistent across the platform, then you see a map which is showing in the middle panel. And the gray color shaded area just shows the night time. So we only have the data during daytime, so that is not shown. Now you can see from this map that over Americas, where you have both East and West and Pacific Ocean, there's a huge every 10-minute coverage. So this area during the time we always have the measurement. Similarly, because of the Himawari over Asia, we always have measurement in the Pacific and over most part of the Asia. Himawari does cover India, but the aerosol retrievals, because of some of the angular limitation, we only cover half of the India for the retrieval purpose. So, and if you can see over Europe and Africa, we still don't have a same quality of the sensors to get a very frequent measure. So once that is done, it is coming in next few years. ESA is going to launch. Once that is up, then we will have a pretty good global coverage every 30 minutes with very high spatial resolution. Okay, so when we combine that same data into daily, then you will actually can get a daily map, which is shown on the bottom panel here. You can see individual sensors are covering, but there's a lot of gaps. And when you combine all them together, you get pretty good coverage all around the world on a daily scale, which can be super, super useful for air quality application because most of the air quality standards are done on a 24-hour scale. Okay, so let's keep moving. Now, I just want to quickly address the air quality issue is that AOD is a column values and then the PM2.5 is measured at the surface. So there are differences between these two quantities. They both are measurement of particles in the atmospheres. One is near the surface, which is PM2.5. AOD is the column of the atmosphere. And they have their own definition, scientific definition. So when we are comparing these two data sets, we cannot just use one for another. We will have to convert them into one from another, making sure we understand the science behind it. So if we have perfect world where we know all the measurements, then this equation basically relates aerosol optical depth, which is typically represented by tau, and the PM2.5, but you need all these supporting actors which play huge roles in making sure this relationship works. And these supporting parameters are nothing but boundary layer height, the particle effective radii, where the particles in the atmospheres, how they are actually interacting with the incoming solar radiations or the wavelength at which we are making measurement. Unfortunately, we do not have measurement or very good understanding of these acting or those supporting actors here, all these parameters. And this is very, very critical. And since we do not know all these players, we cannot really make this correlation accurately. But they are correlated in many conditions. So if you look on the right side, this is a case of fire where there was a lot of smoke was injecting in Northern California in San Francisco Bay Area. And what you see here is the aerosol optical depth on the left, on Y is the PM2.5 coming from the ground measurement. So both does track the change in concentration of the particles, of the smoke particles in the atmospheres consistently. There are differences, and those differences are because we talked about the definition of these. One is column, one on the surface, one is the dry mass, another is under ambient conditions. So these differences may occur, but if we can find way to model these, then we can calculate this PM2.5 using aerosol optical depth. Okay, so like I said, in last, I'll just skip this slide. I'm running out of time. I want to cover a few important things, but just want to make sure that in last 20 so years, we have made so much progress in understanding aerosol optical depth and making its conversion to PM2.5. Unfortunately, we still do not have an operational PM2.5 product at global scale. We do have some regional product, we have some substitute products, but we don't have a global product. And if you look the research here, then you will see there is exponential increase. There are almost 1,000 different publications which actually talks about this problem and have their own solution. So if you divide these approaches which were developed over last 2 decades, then they can be categorized into different categories. So you have satellite derived aerosols. So you can actually use any of these approach listed to calculate the surface PM2.5. And each approach has its advantage and disadvantage. Statistical approach, which include machine learning algorithms, are required to have some kind of ground data so that you can calibrate against. There are model scaling where you actually take global models or regional model like GSChem, GoCard, GEOS, or CHEMS, which does provide a vertical information about the aerosols and assume it is giving you a right vertical profile. You can take model derived ratios of AOD to PM2.5 and then apply that with the satellite derived aerosol optical depth. There are more sophisticated ways to do that is through data assimilation. So you take the satellite data and assimilate or guide your forecasting model so that it has the observation. And then there are hybrid approach where you kind of take any 2 or 3 methods and do step 1, step 2, 3, or you combine their capabilities to come up with most accurate PM 2.5 estimation. So there's a lot of different ways in which people have been doing this kind of analysis. Okay, so very quickly, I'm going to go through some applications which people have been doing, including our group. As you know, the fire season actually is going to start pretty soon in India, northern India, where agriculture fires burns in some of the northern states and produce a smoke which can transport to the long distances and create air quality issues across Indo-Gangetic Plain. So to provide a synoptic way or mesoscale way of air quality from the satellite, last year we actually did some develop a machine learning algorithm based on the data coming from the satellite, not only aerosols data, but the weather data and fire data with some of the ground measurement, and created maps of PM 2.5, which shown on the right. So this is more of a qualitative attempt for us to actually start working on this problem. We are working to validate this product more and making sure that it becomes more operational. Right now, we are just running on a research basis. Then the next thing is that once you have this aerosol data, you can actually put that into a global model. So this one particular example is that we use the MODIS aerosol optical depth in the GEOS model and assimilate the data, and that can actually provide you a forecast or analysis of how the smoke is emitting from one source and transporting to the different places. Okay, so another example here is we used a similar machine learning and GEOS capabilities, a hybrid approach, which I was mentioning earlier, to create a 3-day air quality forecast for Thailand through another project called NASA Surveyor. And this provide an operational, this specific tool is now operational. Thai Pollution Control Department has adopted the tool and actually using this tool for as their operational, and this does provide a real-time capability to monitor quality of the forecast. Another application, a lot of people have used this data for long-term trend analysis. Just showing few example here. These are the aerosol optical depth trends in few states selected, like Rajasthan, where you see a decreasing trend. And number of papers have reported this decreasing trend related to the climate and the precipitation impact in the desert areas. There are states and cities or districts where trends are going up because of the industrial activities or other kind of activities which is happening. And if you look long-term data record, they are very, very consistent. And these trends are not just if you look the numbers, they are very, very consistent. So this provide a solid background in places where we don't have ground measurement, there's something going on. So quickly, let me actually, since I'm running out of time, I just want to cover a few more things. So I'm going to skip a few things. I just want to give you a flavor of what is coming up in terms of the upcoming solar air quality mission. So there is a global pollution monitoring constellation which is becoming available pretty soon in next couple of years. It's a constellation of geostationary satellite. There are 3 satellites. One is GEMS, which will cover Asia. This is already launched last year. It's already providing the data. And the way the system is designed, it makes hourly measurement over this part of the world. Sentinel-4 probably going to be launched in next 1 and 2 years. Tempo is again going to be launched by end of next years. So once these 3 satellites become available, we will have a very good trace case and aerosol measurement at every hours for the northern hemisphere, covering different parts of the world. We still don't have anything for the southern hemisphere. There's another satellite which is going to be launched called Maya, multi-angle image for aerosols. And this is a NASA mission, this specifically designed to actually estimate PM 2.5 and speciation of PM 2.5 on some of the primary targeted areas around the world, which are urban centers. Delhi, Kolkata are one of those selected locations. And the primary purpose of this data is to analyze the health impact of PM 2.5 from these locations. Okay, so just want to quickly review the satellite capabilities. This is a plot provided by a colleague from the South Korean Space Agency, Zoom Kim. On the x-axis, you have a spatial resolution, varies from 0.1 to 1 to 10 kilometers. And then on the y-axis, you have a temporal resolution. And these are the name of the sensors which are either currently in orbits or going to be in orbit in next few years. So in terms of the spatial resolution for aerosols, we have number of sensors which are either already in the orbit, which can provide sub 1 kilometer capabilities of measurement with frequency of minutes to hours. Some of them older sensors have a daily or weekly repeat cycles. And then, like I said, the tempo gems and the other sensor, once they becomes available, then we will have more measurements. So over the time, if we look the timeline of these sensors, then we will see that in last 20 years, we have significantly improved the frequency of measurement as well as the spatial resolution of the measurement. And of course, the accuracies have improved significantly as we continuously improve the algorithms. Okay, so finally, just want to make sure again that these three components of air quality management are critical part of any air quality research, monitoring, or forecasting, and they go hand in hand. If we have only one of the component, then we can only do so much. But we have capabilities and expertise in all these three components, then there's a lot more science question, and there are a lot more policy decisions can be made using a hybrid approach. And I think that's all I have. I'll just leave this slide for people to see. This is just a view from Himawari looking some of the pollution over Indo-Gangetic Plain. And that's all I have. Thanks. Sorry, I ran over a few minutes extra.
Yeah, thanks, Pawan, for a very nice, fantastic overview talk. How to use satellite, low-cost sensors, model in an integrated way. I think that's the way forward, because one particular tool cannot give all the answers. So every country should actually adopt this hybrid approach of monitoring, particularly the lower middle income countries where the ground-based monitoring is enabled. So the floor is open to questions. There are a few questions in the chat box, but just want to test Mr. Duggal if you want to ask any question.
No, Sagnik, I'm fine. Very good presentation. Thank you very much, Pawan.
Thanks.
So there was a clarification question. I think, Pawan, in some of your slide, there is the equation. So somebody asked, Saksham Bhatia asked, like, what is the implication of there is a parameter M? I think that's the air mass you are talking about, most probably.
Oh, are you talking about the equation for aerosol optical depth?
Most probably that's because the question is just written, what is M in the equation? I think probably.
Oh, that is, yeah. That is air mass, which is calculated using the position of the sun. So if you take the solar zenith angle, because you want to calculate how much path solar radiation had crossed the atmosphere, and it is not always to the at the zenith, because satellite is looking at certain angle as compared to the sun. So you need to calculate where the sun in the space to actually account for the column of the atmosphere.
Okay, so there is another question about the remote sensing of aerosols versus trace gases. So basically the question is that while most of the aerosol sensors have good spatiotemporal resolution compared to the trace gases sensor. So is there any reason for that?
Yes, so excellent question. So I think I briefly mentioned that most of the aerosol measurements happens in the visible part of solar spectrum. We use the visible part of solar spectrum around blue to red channels, and we have pretty good signal there. And the bandwidth of those channels are 10 nanometer, 20 nanometers. So you have a consistent signal from the aerosols because of their size and their optical properties in that range. So you get good signal. When you're trying to get the trace gas retrieval, as we know from the basic understanding of their properties, that gases doesn't respond to the entire solar spectrum in the same way as aerosol does. Gases mostly does absorption of these particular wavelengths. So these wavelengths are very, very fine lines of spectra with less than 1 nanometer. So you need a specific type of measurement which are very high in spectral resolution. So when we talk about the aerosol, we can live with 10, 20 nanometer resolution or 40 nanometer resolution. But when we need to make gas measurement, you need to have very specific measurement at 1 nanometer or less than 1 nanometer spectral resolution. And most of these wavelength actually which responds to these trace gases for ozone, for example, they are in UV part of solar spectrum. And as we know, there is a very little UV which actually pass through the atmosphere and reaches to the surface. So in order to acquire enough signal for that particular gas measurement, we have to average over larger area. And that is one of the reason the spatial resolution of UV measurement or trace measurements are coarser compared to the aerosol measurement.
So there is another question. I think this is also a good question from Palash. So he's asking how can cities and urban local bodies effectively use remote sensing to improve air quality, particularly from the regulatory point of view? Can they be used to identify particular source or hotspot?
Yeah, so I think that's an excellent question. And different people have probably different view how to use that. First is you, depending on the size of the city, definitely satellite, if there are no ground measurements available, definitely we can use the satellite data to look and identify for specific pockets of the city where hotspots are located. We may not be able to pinpoint the source of those pollution, but we will be able to probably look for the hotspots. For example, in city of Delhi, we probably can map where the major hotspots are there using the current 1 kilometer AOD data, or even 2-3 kilometer data of tropomy, which provides like NO2 and SO2. So those things can be used. The second thing you can do is, since we have a long-term data records, like 20 years plus data records for aerosol, we can also look for trends, how things are changing from year to years. And that has a policy implication. Are those trends are because if, for example, let's say one city has implemented rigorous regulation to control the pollutions through different mechanisms, was it effective or not? So if you don't have a ground measurement, you can actually look long-term satellite data. And we have seen these cases many times in US and China and many places where they have worked rigorously actually to reduce the pollution, and it does shows up in your satellite data. Now, if we are talking about the daily monitoring and regulatory purpose, then I think we are still not there in terms of using satellite data. There are a lot of uncertainties which we do not understand. There are steps which needs to be done. Data needs to be carefully analyzed to do that kind of a study. So I think I would say on a regular basis, on a daily scale, if you're talking about the regulatory uses, then it's still we are a little bit behind on that. But for long-term policy decisions, for making even for putting a new monitor, you can use the satellite data to look for the location where the ground monitors can be put, because you can identify source hotspots in cities in places like that. I hope I have not
Yeah,
confused more than answered.
sure. So, in the interest of time, the last two questions I will take. So, one question is technical, Pawan. So, the question is basically if you compare the Modis 3 kilometer and 10 kilometer product, uh, 10 kilometer product actually has a better accuracy. So, why is that?
Yeah, so I think the initially when we developed the algorithm and when we did this, so the algorithm was done even pre-launch of the satellite. Okay, so at that time, before Modis was launched, our understanding of the aerosols is that it is a difficult problem. We only had some measurement from AVHR type sensor, which has a huge band all the way going from blue to red or near IR. So we used to, whatever understanding of retrieving aerosol we have from that perspective only. So the fear was in the beginning that we probably not have enough signal to noise ratio to actually retrieve aerosol at very high resolution, like 250 meter or 1 kilometer or 3 kilometer in the beginning. So that's why people who developed the algorithm, they started with the 10 kilometer, they did some sensitivity analysis and they figure out, okay, this is a sweet spot. We can start with 10 kilometer. Over the year, we realized that 10 kilometer is not sufficient resolution, and communities, specifically air quality community, demanded for the higher resolution product. So we adopted the same 10 kilometer algorithm on a 3 kilometer product. So now remember, we are using exactly the same algorithm, same cloud masking, same models. We have not done anything different in 3 kilometer. So when you go to the 3 kilometer, obviously you are reducing the signal to noise ratio, because now you have lot less number of pixels to do the cloud masking, to characterize your surface, to remove the pixels for cloud shadows and other factors. So you are dealing with very less number of pixels, and that can create a lot more noise in the data. And that is why our 3 kilometer product is, I would say, less accurate compared to the 10 kilometer. Now, but we can argue that there is a Mayak product which is at 1 kilometer resolution, which is even higher than 3 kilometer, but it has almost same accuracy as that 10 kilometer product. Why is that? And that is a completely different approach. So you have to remember that when we talk about 10 and 3 comparison, we are talking about the exactly same algorithm. Mayak is a completely new algorithm specifically designed to do retrieval at 1 kilometer. It has different assumption, it has different science, it use completely different approach to do the surface reflectance characterization, and that is the reason it is able to provide more accurate AOD retrieval. So it in a way it has something to do with the historical way in which we have done things in dark target. Newer algorithms are able to get more accurate results than what was done at 20 years back.
Yeah, so I will. This is the last question in the interest of time. Again, it's a good question. So basically, in your talk, you focus mostly on the air quality, but can you quickly give some idea how these remote sensing datasets are useful for climate studies? So there is a lot of interest now after the IPCC.
Sure, sure. Yeah. So actually, that is very interesting because when Moody's was launched and the aerosols data were actually developed, the primary purpose of aerosol product development was to study the climate. It was never, air quality was never focus for aerosol optical depth. It was just after the fact people started using for air quality. So in the beginning, in last first 10 years or 15 years, if you see the research studies, then you will see most people use aerosol optical depth either into uh, global models to assess the radiative forcing due to the aerosols. They have IPCC heavily used now MODIS data to actually quantify the radiative forcing of aerosols. Model uses that frequently to actually look for the trends in temperature cooling and warming in different parts of the world. Uh, we have done a lot of studies in the beginning where we actually combined the aerosol optical depth data with radiative forcing data coming from series instruments or other ground measurements to actually assess how much radiation is either absorbed or blocked by these aerosols in different parts of the world, what is their trends and things like that. More recently, we have some of the measurements which can provide the vertical profiles of the atmospheres from like Calypso. So if you combine the Calypso with radio transfer codes or climate model, then you can actually calculate the profiles of temperatures in the atmosphere and how it changes as function of change in aerosol concentration. So that is short answer.
Yeah, thanks, Pavan. So it's now my turn to propose the vote of thanks to end today's proceedings. So first, I want to thank Mr. Arun Duggal, founder of SARCA, which is now renamed as Arun Duggal Center of Excellence for Clean Air Research, for always being there, supporting SARCA in all the activities, being so passionate about air pollution. And now, actually, the activities have expanded to include climate change as well. So thank you, sir, for always being there. I also want to thank all the participants who joined today, despite today being a national holiday. It's really encouraging to see so many participants joined in. That too in the evening at 5 p.m. Indian time on Friday. Really, it tells that how people are passionate about air pollution in the country, and I'm sure Pawan, your talk will illuminate them, encourage them to further take up research in this area. And finally, a big thanks to you, Pawan, immediately agreeing when I requested you to give this seminar. We have been working, and we look forward to work more with you in future. Thank you again for being our speaker today. So this ends today's proceedings. So good evening, everyone. Stay safe. Take care. Bye-bye.
Thanks, Agnes. Thanks, Mr. Duggal and Priyanka for organizing and giving me opportunity. Thanks, everyone, for attending.
Thank you.
Have a nice evening.
Bye-bye.
Bye-bye.